Okay, so we got to wrap up the last slide or so, and then we're going to draw. All the way from here. So this thing here. So sometimes you get these sort of, we were going over free body diagrams. I don't know, little transition here. I don't know what you were doing before. Sounds like linear calc. Okay. And we've been going over free body diagrams. You know, how to figure out what all the forces are in these objects and stuff, and the reaction forces, as well as the external forces. And we've been looking at how to sort of pick apart something to kind of show the forces acting on. Generally, we just pick the one main part of the problem, which is sort of common to everything, like this big beam here, which is supporting everything. And we look at the forces inside there. Sometimes you get a system, you know, where you have multiple bodies, just like those like hanging chandeliers where you had two chandeliers and stuff, and you had to kind of solve the problem at one point, move to another point. You're going to also kind of get those things too. So situation where you have two of these big pipes or whatever they are on a forklift, and you want to know, you know, we want to be able to figure out all the forces acting on that thing, on those pipes. We can take each one separately, and we can take them as a whole. If you think about the load as one thing, you would realize, you know, you're going to have a weight of cylinder B, and the weight is sort of acting right in the center of gravity of the body, even though there's no material there. I'm going to close. And then you have the weight of cylinder A, right, going right through its center of gravity. And then what would be the reaction forces acting on those pipes? What's keeping those pipes from falling through the fork? Perpendicular normal force is acting from the surface of that fork towards the center of the body, right? They're actually contact forces. They're actually pushing. So there's like a normal force for pipe A. I guess we're going to just call these, because there's actually two forces on this one. We're going to call this N1, N2, and N3. So that's the system as a whole, right? But then you could also take apart the system and look at the different pipes individually. And if you look at the first pipe, then it's got this WB. Sure, it's going to have this N3 here, but it's also going to have a normal force pushing from pipe A to B. We could call that NAB. And that's kind of, now, you know, we're taking out that pipe, so we're just isolating that one little piece of the system. And now we're looking at forces that, this NAB force would be sort of considered internal to the total load, if we just think of that total load as one thing, right? That would be considered internal force, but we can break it apart if we need to find those forces in between. And then, of course, the other pipe, A, would have its N1 here and N2 here. And then it would experience the equal and opposite NAB going. Let's call this NBA going from B to A. And again, that's coming from this now invisible pipe there. So that's just the kind of thing about, you know, breaking up forces. Kind of applying our reasoning skills from physics to kind of figure out what those reaction forces are. There was one more quiz here. Internal forces are not shown on a free body diagram because the internal forces are you say D? Yeah, they're important, but they're equal and opposite. They don't affect the external calculations, right? So the kind of calculations we're trying to do on that free body diagram, the internal forces don't matter. So if we're looking at this problem here and we just want to know, what are these normal forces on the, we can generally, we can take those things. Well, actually, the reason, this is actually kind of interesting. So let's see, the problem with this one is you kind of have too many, you've got these sort of parallel forces. I don't know if you could actually solve, sometimes with a system like this, the way these forces are aligned, you may not be able to solve them when they're together. So we break them apart. When we break them apart, there's only two unknowns on each cylinder, right? So, well, there's two unknowns on this one, and then you can take this result and feed it back into this one, right? So you can do these kind of fancy things. But again, we're looking at the bodies as units and internal forces in general. Well, always, we never look at the internal forces. We always look at, if we do look at internal forces, we draw them so that they're external. I'm talking too much about this. I hope that makes sense. So this one, how many unknown support reactions are there in this problem? Okay, we just went over these different supports yesterday. Maybe you forgot them, but there's something going on at A, something going on at B. What's going on in there? How many total reactions, unknown reactions are there? Okay. Karen, how many forces do you think unknown reactions are there? They could be forces or a couple moments. Okay, let's see. Who else? Joel? 3 forces? Okay. And what would they be? A force pointing this way at A, yep. But can it, what is this thing at B? It's not a pin, it's a roller. Okay, and remember what rollers can do? A normal, right? Perpendicular normal force, yeah. So you can get only this, you can call this N sub B. Okay, that's 2 forces, so we're going to have this A sub X. What else anyone see? Sorry? A sub Y, yep. Okay, what else? Anything else? A couple at A. Couple at A, right? Because it's a fixed support. Remember, a fixed support goes into a wall, and that wall itself is going to be, however that works. I try to draw a picture of that. There's sort of a force here, providing the couple there that's keeping this thing from dropping. Now, the thing is, there's also the support at B, and the other question you might ask is, can you solve this, right? You've got how many unknowns here? 3 forces and 1 couple moment. That's 4 unknowns. Can we solve that? Problem with 4 unknowns in 2 dimensions? Well, no, we can't, because we can only solve for 3 forces in 2 dimensions, or 2 forces in a couple, or those kinds of things. So we can only solve for 3 unknowns. And actually, this problem is considered statically indeterminate. Does anybody see why? The couple could equal 0 if NB is actually taking all of the load of this thing right? Like this couple moment is needed at M. I mean, this MA moment is needed in order to keep the thing from collapsing down, right? But if you've got this support NB that's able to do that, then the couple moment at A could be 0. Or if somehow it was just adjusted that this wasn't quite high enough, maybe there's a little, like an air gap in between there, maybe that's actually not even touching, then this normal force at B would be 0, and the couple moment at A would have to take all that load that's trying to make it trying to make it collapse, right? So, and you don't know, it could be anywhere in between based on how these things are adjusted. So it's considered statically indeterminate, which I'm not a structural engineer, but I think they try to design things so there isn't any of that indeterminacy so that you actually know what all the structural forces are. So you would maybe change this fixed support, but I mean, actually this could be also redundancy, right? So I don't know. We should ask Matthew. Matthew, the civil engineer, is going to be talking to my intro to engineering class on Thursday. He's a structural engineer. He does all these things all the time. 4 to 6. Yeah, if you want to come by Thursday. He's a really interesting speaker. Anyway, questions anymore? I'm going to kind of move on. I think we nailed that one. And now we're going to move to the next one, which is actually solving these problems. Okay, the first one was kind of conceptual. Now we're going to apply these equations and solve for the unknowns. And we're going to also recognize, we're going to try to recognize when there are two force members. Does anyone see a two force member on this diagram? It's hiding in plain sight on that front page. What two letters define the two force member? B, C. Yep. That's a two force member. Because it's only attached to the other structure at 2 points. So it's a two force member. There's another one right here, but it's not labeled. 3 scalar equations, some of fx, some of fy, some of m0 are most commonly used, yeah, not always. And a rigid body, subject to forces as shown, can be considered a two force, but there's 6 forces on it. Yeah, the net forces are 2 points, so that's a 2 force member. There's only 2 points where forces are being applied to it. If it's in equilibrium, those forces have to be equal and opposite, pointing away along the line AB, which I didn't really draw very well. So we are now going to be able to find the forces on the joint at A and the link at C, keep that cherry picker up in the air. We'll be able to figure out what's going on where those things are resting, that beam is resting on the walls there, and other stuff like that. So a body subject to the forces in equilibrium, the net force and the net moment have to be 0. So the sum of all the forces in x and y and the sum of all the moments about O, or any point in there, O could be anywhere, could be there, have to equal 0. And these are the most commonly used, but not always the best. Sometimes it's easier to do the sum of moments at 2 different points, as we'll see either this week or next. So the steps for solving problems is one, you want to establish a suitable XY coordinate system. Sometimes if the problem is tilted, like that forklift with the 2 pipes on it, you might want to tilt your coordinate system. The second thing is, of course, you always, always, always draw a free body diagram of the object under analysis. And apply the 3 equations of equilibrium to solve for unknowns. If you have more unknowns than a number of independent equations, then we consider that, like I mentioned before, statically indeterminate. You can't solve these problems using just statics. Yeah, there is a solution, but we can't really know it with just statics. And the order in which you apply the equations may affect the simplicity of your solution. If you have two unknown vertical forces and one unknown horizontal force, solving Fx equals 0 first allows us to find the horizontal unknown quickly. And as you'll find, if the answer for an unknown comes out as a negative number, that means the sense of the unknown force is opposite to that assumed in starting the problem. And we'll talk about that and what that actually means in a second. So here, this one, determine the reaction forces at A and B if each force is 5 kilonewtons. And we're given these distances A, B, C, and D. So A is 2, B is 3, C is 2, and D is 1. So I'm telling you, okay, so we're going to need to find, so these are the reaction forces already labeled AX, AY, and BY. So this is AX, AY, and BY. And we've been telling you that the most common equations of equilibrium are Fx, oops, the sum of Fx, let's just do a comma there. The sum of the Fy's and the sum of the moment about some point equals 0. That's the most common, but in this very first problem, we're gonna do the second most common, which is taking moments at different places. It turns out that that's actually quite easy too, because the sum of the moments at 2 different points can give you these two vertical forces, AY and BY, with less algebra. So let's start by taking the sum of the moments at A equal to 0. This will help us find which force? BY, yeah. So the sum of the moments at A equals 0 is going to equal, okay, so we've got each force is 5, so it's going to equal 5 times 2 negative, right? And then we've got a 5 times 5, which is also negative. And then we've got a 5 times 7, right? We're just taking each of these forces by its related moment arm, and all those moments are negative about point A. And then to that, we're going to add BY, and the moment arm of BY is going to be 8. And in one equation like that, very simply, we find a really easy equation to solve for BY. So BY is going to equal 70 over 8 kilonewtons. What about AY? We can do the same thing by finding the sum of the moments at B. And cutting to the chase, we can say, well, that's 5 kilonewtons times, let's see, we're going to have all these different distances. Like now to B, we've got 1, 3, and 6. We're going to say 1 plus 3 plus 6 meters. Those are positive, going counterclockwise. Actually, going counterclockwise, and then minus AY times 8 again. And therefore, AY is going to equal 50 over 8. So I solved that pretty easily. And our last sum of Fx equals 0 means that Ax equals 0. So that's our third unknown force. And that's it. We could, if we wanted to, do the sum of the moment at C equals 0. But there is no new information. Won't help us solve anything. We could do the sum of the moments at D. At D? What? Oh, I'm sorry. We could do some of the fy's equal to 0. But again, that's not going to give us any new information. But instead of doing the sum of the moment at B, you could have done the sum of the fy's equal to 0, and then you could have solved for ay that way as well, right, if you wanted to. So there's actually more than one way to get to all the unknowns. There's a lot of equations you can choose from. And all you got to do is find the ones that get you to the unknowns, generally with the easiest amount of work. Questions? Okay, what about this cart that was hanging at the end of the oil platform, or hanging on the oil rig or something, right? This platform. What if we need to determine the reaction forces at A and the tension in the cable, given that the weight is 3 kilonewtons? So we have to find AX, AY, and TB. Okay, there's the only known force acting on that is the weight, and the weight is given as 3 kilonewtons, and its location is given, at least its location horizontally from A, is given by those dimensions below it. So in this case, we might decide, with those beam problems, it's pretty common to do 2 moment equations, because all those forces are acting on a line. It's really easy geometrically. You've only got that one unknown that's going to apply there. Some problems are a little less linear like that. This is sort of one of them. So in this case, let's start with the sum of the fx's equal to 0. And that's going to give us, let's see, it's going to give us AX and minus TB cosine of 70 degrees, right? Because that's the x component of TB pushing back at AX, right? Some of FY's, let's see, audience participation. Let's see. Zeki, you want to give me a Y force here? That sounds good. A sub Y. Connie, you want to give me another one? Minus TB sine of 70. That, I like a lot of that, but there's one thing I would change. Yeah, it's going up, right? Plus. And Z is another Y force. Minus W. Yep. Which we could just list as W for now, and we'll change that to 3 kilonewtons in a second. Okay, now we have to do at least one moment calculation in all these 2D problems. The question is, where do you want to actually do it? Where do you want to do the moment calculation? At A? Yeah, why don't we look at that? We could do the sum of the moments at A. And what forces, let's see, extra challenging here. Joel, you want to give us a moment, something that's giving us a moment at A? And I would recommend, if you're looking at this tension, to think about that in terms of the Y component and X component. Yeah, W times 1.4, is that positive or negative? Yep. Okay, Manuel, another moment about A. Yeah, TB sine of 70, that's the vertical part, times 2.2, that's the distance to A. Positive or negative? Okay. And Jonathan? There's another one. That's it? Anyone see any other ones? Victor? Yeah, there's also the TB cosine of 70. What's the moment arm? Times 1. Positive or negative? Yes. Yeah, that other one there hiding up there, right? Gotta search them all out. Because that too is going to provide a moment about A. Okay, so that's one thing you could do. And actually, is this a complete set of equations to solve all of our unknowns? Do we need another equation? Basically, you have 3 unknowns and 3 equations involving them. So yeah, you could solve them right now. So in fact, if I was doing it, I would solve for TB first, right? You could take the last equation and solve for TB directly, right? But just for the sake of exploration, where else could we do a moment? At B. Okay, let's just experiment. What would that look like? Trent, how about a moment about B? Wait, times 0.8, positive or negative? Yeah, I think it's positive. Yep. Okay. Aziz, another moment. AY times 2.2, positive or negative? You sure? Positive or negative? You still thinking positive? Okay. Why? Yeah, we're going to call that our positive direction. And the sense of AY about B, you're saying is counterclockwise? You have this water wheel here? Yeah, it's actually clockwise, so it's negative. Yeah. Got to be careful with those. And Corey, another moment about B. Uh-huh. Positive or negative? Which one? Okay. So if you were a river flowing towards B and you noticed a wheel, a water wheel in there, which way would that wheel be going? Counterclockwise, which we're calling positive, right? Yep. Okay, that's the second point. We could conceivably do a moment at G, but we don't know the vertical location, so it's going to be a little bit hard to figure out that one. So that's a problem. So we can't really do that. But at least you have 4 options of equations, and you have to use 3 of those to solve for the unknowns. Back to our brake pedal thing. What is the applied force that causes the spring to stretch by 1.5 inches and creates a force of 20 pounds in link B? Well, we may get problems involving springs. It's still static. Find F. Oops, colons are there. Find F given that Bx equals 20 and S equals 1.5 inches. Well, what does it mean when the spring has stretched by 1.5 inches? What's the force there? Well, Hooke's law, Fs equals Ks. K being 20 pounds per inch. Times S 1.5 inches is going to give us 30 pounds. So that force on the spring has to be 30 pounds. Well, having done that, we could find the sum of the moments. Well, we just, in this case, actually, this is kind of a good question. You know, if we're just trying to find that force F, do all agree that the place to do that is to find the moment about A? If you're just trying to find force F, and they're not asking for what AX and AY is, and it's not, you can just go straight to finding the moments about A. You're going to solve for F directly. AX and AY don't count. They don't give you a moment about A, so those unknowns can be ignored. And you can write a single equation to get to the answer. So we sum up all the moments about A. Alex, do you want to give us a moment about A? Sorry, say that again? AY times 5? But we're doing moments about A. And AY is acting right at A, so the contribution of AY would be 0 to the moment about A. How about another force is giving us a moment? A sense of rotating, a force that's going to make the thing try to rotate about A. Yeah, you've got Fs times 1, and is that positive or negative? Okay. Adrian, another moment about A? Some force that's going to cause a rotation about A. Karen, can you help them out? Sorry? Bx? Did you say negative Bx? Okay. Is that it? That's a moment? Times 2.5. Good. Yeah. Good. Adrian, there's one more moment about A. Can you see it? Paula? Yeah, F times 5. Positive or negative? Okay. Yeah. So you can now solve for F. So this tells you that F is going to equal 30 times 1 plus 20 times 2.5 divided by 5, or F equals 16 pounds. So we're done at this point. But if we were asked to find AX and AY, what would we do? How would we do that? We would use the sum of the fx's equals 0. By the way, I really want to see you write the sum of fx equals. A lot of people just like start writing equations, and I don't really know. When I'm looking at it, it's hard for me to know what your equation is supposed to be representing. So I want you to write sum fx equals 0 when you solve these. Okay, people are laughing. This is how you create neat solutions that I can track a lot easier. Sum of the fx equals 0 is going to give us ax, going to give us fs, going to give us bx, and therefore ax is going to have to equal minus 50 pounds. Sum of Fy equals 0 is going to give us Ay minus F. So that means Ay is going to equal 16 pounds. Okay, questions? Okay, back to our pipe problems. Each pipe weighs 3 kilonewtons. Determine the reactions between the pipes and the forklift. Okay. Well, again, we looked at how to break these things up and kind of talked through that just a little bit ago. We have to find N1, N2, and N3, given that W1 equals W2 equals 3 kilonewtons. And we've already broken this thing up into 2 separate problems. So we're going to look at that first pipe, which only has 2 unknowns on it, and write, well, first of all, we're going to say, well, remember we had to choose a good coordinate system. And for this one, it'll sort of be a lot easier, I think, if we tilt the x, y axes so they look like that. Because then we only have one force that's at an angle. It makes it a little bit easier. I don't think you have to, but it makes it easier. So the sum of the fx is equal 0 is going to be NAB minus W, but it's the x component of W, so we'll have to break W into a y component and an x component. And where basically, let's see, yeah, this is 30 degrees, so basically, yeah, you can draw that rectangle. So this here is 30 degrees. I should be able to see that. So this is Wx, meaning that NAB is going to equal Wx, which is going to be 3 kilonewtons times the cosine of 60 degrees. And that's going to equal 1.5 kilonewtons. The sum of the Fy's equals 0 is going to equal N1 minus Wy, giving us N1 is going to equal 3 kilonewtons times the cosine of 30. Which is 2.6 kilonewtons. So that solves the 2 unknowns on pipe 1. Now we can kind of look at pipe 2. And in pipe 2, we've got the NAB force and acting the other way. So the x's are going to be, we're going to have an N3 minus Wx minus NAB. So that means that NAB, well, I'm sorry, NAB is already found. NB is going to equal 3 kilonewtons. And the sum of Fy equals 0 is going to give us N2 going up minus W sub y going down, and therefore N2 is going to equal 2.6 kilonewtons. Again. Okay, that's the, yep, question? Pardon me? Yeah. Because the axis is tilted, we have to compute, we have to resolve W into the X and Y axes that we've angled like this. It just sort of makes it easier to solve. Yeah. If you don't do that, then you're going to have a more complicated system of equations, because both, like, if you look at it, you know, if you just did the sum of x's going in this, you know, where x is going this way, well, the W component is 0, but you're going to have like an N1 with an angle, you know, cosine of some angle, or, you know, and then NAB with cosine of some angle. So both of those unknowns will appear in the same equation, making it harder to solve. If you tilt them, then each equation only has one unknown. Getting back to some more concepts, for this beam, how many support reactions are there, and is the problem considered statically determinate? Sorry? Well, there are 3 supports there, right? So you can kind of pretty much guess that there's going to be 3 support reactions. Is it considered statically determinate, though? That means, can you find out what those forces are? Yeah, you can't really tell, you know. And is it actually stable? If those are rollers, is it stable? No, it's going to just roll right off, right? It should, right? Yeah, and with 3 vertical forces, you know, what equations could you use to solve for 3 vertical forces? You could do the sum of the Fy's. Well, maybe sum of Fy's equals 0. You could do the sum of the moments about like this point here. I don't know. I think it's indeterminate, but I guess I have to prove that to really convince you. Well, actually, maybe not. I don't know. Maybe I can look at those. Maybe it is determinate. Let's see. Well, let's look at the second one first and come back to that. Suppose you have this beam, and it's supported by a fixed support at A. Remember, this is kind of, it's going right into the wall. And whatever this is, you could say this is a pin. And how many support reactions are there on the beam? First of all, how many support reactions would you be able to come up with? 5. What would they be? A Y, a X, the moment, because it's a fixed support, and 2 on this one. But it's a 2-force member. If this is actually, you know, pinned on both sides, it doesn't really tell you that. If it's pinned on both sides, if it's not pinned on both sides, then yeah, you would have 5 forces. But if it's pinned, it's a 2-force member. The direction is going right along that beam there, and we just don't know the magnitude. So we got 1, 2, 3, 4 unknowns, reactions. Is it statically determinate? Remember, 2D problems, how many unknowns can you solve? 3. So with 4 unknowns, it's indeterminate. It's like you have a what's that called when you have more unknowns and you have equations? What does they call that in linear algebra? Like the uniqueness and existence of solutions, right? It has many solutions, right? Yeah. What's that called? There's a fancy math term for that. I don't know. Under constrained? I don't know. It's like an under constrained system. Anyway, but is it stable? Is it going to move? I mean, assuming that all the pins hold and everything. But yeah, it's stable because every force has a counterforce, right? The horizontal part of this force is being met by AX, right? The vertical part is being met by this guy. Yeah. You have over supported it, which is fine. You just can't figure out what the support reactions are going to be at all the point. Like that other problem, you could have a moment, or if this is taking up all of the tendency to rotate, then you might not need an MA there. So the answer is B, tricky one. And let's see if we can see if the answer for 1 is meaningful. The answer for 1 is D. In other words, it is not determinate. And I think it's because the forces are all in parallel. Well, we're running out of time, but there's one more concept, which is, again, touching on 2 force members and 3 force members. And I think we'll kind of talk about this, and then I'll show you one more solution. So you got to burn this into your head. When you see a body that's only attached at 2 points, you got to say 2 force member. That simplifies the solution because when you see one of those, that means you only have a single unknown. You know the direction of the force, you just don't know the magnitude. So that really helps. It doesn't matter if the object is in a straight beam shape or if it's in an L shape or a semicircle shape. It's still a 2 force member where the direction of the force is oriented between the 2 points of attachment. Okay? The force has to be oriented along that line, otherwise it will actually move. Right. So this AB is a 2 force member, right? This AB here is a 2 force member. Again, assuming that it's small enough that you can neglect the weight. If the weight is a consideration, then yeah, you're going to have a 3rd force acting on it. But according, you kind of think about it's sort of a level of significance. If it's got, a force that's 100 times more than its weight, which is common, then you can ignore its weight. So this is a bit involved, but you're going to get to do like a backhoe problem at some point. I don't know if it's this week or next or later, but anyway, the weight of the boom is 125 pounds. That means you've got a force here. And we need to find the support reactions at A and B, A being a pin, B being a pin, but it's connecting to a 2 force member. So there's only one unknown at B, right? There's just FB. But there's an AX and an AY acting at A. And those are the 3 unknowns. So the free body diagram looks like that. And is this on your handout? No, yeah. So anyway, it's just like the problem we did with the platform, pretty much. These problems are very repetitive. You're doing these over and over again until you have a pretty good understanding of it. Which equation of equilibrium allows you to determine FB in this particular problem right away? Some of the moments at A, because you can just eliminate those A forces, right? They don't have any moments about A. And A beam is supported by a pin joint and a roller. How many support reactions are there, and is the structure stable for all types of loading? Did you say B? Yeah, B, right? There's 3 supports. And if you put a loading on it like that, it's not going to be very stable, right? So it is not always stable. It kind of makes you wonder, you know, are the bridges, could they potentially, if they're really supported by rollers, will they go flying up? I don't know. Hopefully not. We may have to investigate. Okay, that's it for today.